Welcome students. In this video lecture, we are going to learn about one-dimensional wave equation and its solution using method of separation of variables. Now exactly before starting the mathematical portion, let us have a glimpse of the various waveforms in actual real life so that we will understand the necessity of studying the one-dimensional wave equation. So these are few pictures of waveforms, especially in medical field. These are the arterial pressure waveforms, and here we have a glimpse of the waves of blood pressure and oxygen saturation, etc. ECG in the ICU unit. And this is waveforms of ventricular depolarization and arterial depolarization. And here we have pressure waveforms. Similarly, here we have pulse waveforms. So you can observe the various forms attained by the heartbeat, etc. And here we have the glimpse of brain waves and heartbeat waves. So if you observe several characteristics in medical field are expressed as waveforms, so it is essential to study the wave equation and the final solution, what does it represent, etc. These are again, here we have respiratory waveforms. Now let us consider transverse vibrations of a string of length L where the two ends are fixed, and we take one end of the string x equal to 0 as origin and the equilibrium position of the string as x-axis. That is, when the string is not having any displacement, that horizontal position we take as x-axis, and the line passing through origin and perpendicular to this x-axis will be the y-axis, and that is how we create the xy plane and we observe the motion of the string in this particular xy plane. You can see this picture. So here this 0, this will be the one end of the string, and this line will be the equilibrium position of the string, and here y represents the displacement of the string at a distance x and at time t. And we have few assumptions in deriving one-dimensional wave equation. These are the few points you can have a glimpse. The motion will take place only in one plane, which is the xy plane, and the tension T will be constant. Effect of friction is negligible, and the gravitational force will be neglected, and slope of the deflection curve is small. So these are a few assumptions we make in deriving the one-dimensional wave equation using the method of separation of variables. So under all these assumptions, the one-dimensional wave equation is actually derived as, this is the main one-dimensional wave equation, dou squared y by dou t squared equal to a squared dou squared y by dou x squared. Students, actually we are not exactly deriving this one-dimensional wave equation because that is not our aim. We concentrate more on applying the solution of wave equation and getting the solutions for real-time problems. So we do not actually go to the derivation part. And when you observe here, y is the main function which represents the displacement, and it is a function of x and t, where x is distance and t is time. And this constant a squared has a specific value which is tension by mass, or in short it is represented as T by m. When we derive the solution of this one-dimensional wave equation by this particular method called separation of variables, we will come across three different cases, and hence we will have three different solutions like this. So when you observe these solutions, you will have one in terms of x, another function in terms of t. So all the solutions will be of that form. That is why it is called method of separating the variables. And of course, among these three, we need to select one particular solution which is most suitable for vibrations of a string. And vibrations of a string will be always a periodic. Like you can observe, waves will be periodic. They will keep on coming back to the same form. So among these, which will be the periodic function? Yeah, cos and sine, we know that cosine and sine functions are periodic with period 2 pi. Hence, the second solution will be the most suitable or the correct solution of one-dimensional wave equation. So this second solution will be the correct solution of one-dimensional wave equation. Now let us see a problem how to solve one-dimensional wave equation. A string is stretched and fastened to 2 points at a distance L apart. Motion is started by displacing the string into the form k into Lx minus x square, from which it is released at time t0. The question is to determine the displacement. So now let us see how to solve this. First, let us write the one-dimensional wave equation. Already we had seen this. Y is displacement, x is distance, t is time. And of course, this is the correct solution. We are taking and writing the correct solution here. And before moving on to the solution, we need to write the boundary and initial conditions. These 4 will be the boundary and initial conditions. Now let us see how these 4 conditions comes one by one. Look at the first one, y of 0, t 0. How this comes? Actually, this word says the 2 points x equal to 0 and x equal to L, the 2 end points of the string is fastened. What is the meaning of fastened? Tied up. So you can observe, this is one end x equal to 0. This is the other end x equal to L of the string. Both the ends will be tied up. Tied up means at x equal to 0, there is no displacement. The string will not have any motion. Similarly, at x equal to L also, the string will not move. So at x equal to 0, the displacement is 0. At x equal to L, the displacement is 0. So that is why you have the first 2 conditions. Now the third will be initial velocity 0, because they have not given any velocity, and of course the string is displaced from rest. So the initial velocity will be 0. Why this is initial velocity? Because y is displacement. Velocity means rate of change of displacements, dou y by dou t. And the word initial means time 0. Starting time. The word initial always denote starting time. So starting time means t0. And the last is initial displacement. They have given in the problem. The string, the motion is started by displacing the string into this form. So this is known as starting form or the starting displacement. So that is why you have this as the starting displacement. So y is displacement. The word starting means initial, and hence you have t0. So there are 4 conditions here. Now let us apply these 4 conditions one by one in this correct solution. So now let us take the first condition, y of 0, t 0. What is the meaning of applying this? In the place of x, I have to put 0. In the place of x, I have to put 0. So go to the correct solution. When I put x 0 here, what I get? Cos 0, 1, sin 0, 0. And we should not touch t because t is t only. So don't touch the t term. So here you have the first answer will be C1. First term answer will be C1 into second term. And the condition says that is equal to 0. And when you have this equal to 0, you cannot equate a term having variable. Here this term is having variable t. So don't touch that. So what has to be 0? C1 has to be 0. So this is the first result we get when we apply the first boundary condition. Now let us go to the second boundary condition. Y of L, t 0. Now put L, t means in the place of x, we have to put L. So this is the correct solution. And in the place of x, substitute L, C1 cos PL. But C1 is already 0. We got C1 0 here. So don't write C1 term here. So C2 sin PL into the second term is having t. Don't touch that. The condition says this answer is going to be equal to 0. So which we need to equate to 0? The term having variable we should not touch. So C2 sin PL has to be 0. It means C2 can be 0 or sin PL can be 0. But if we take C2 0, already C1 we got 0 here. So if C2 and C1 both if they are 0, if you substitute C1 and C2 both 0, the full answer will become 0. So the entire y of x, t will become 0, which is actually called a trivial solution. But we do not need any trivial solution here. So you cannot take C2 0. So the other possibility is sin PL has to be 0. And remember sin n pi 0. So comparing sin PL 0 and sin n pi 0, what you have? PL equal to n pi or P equal to n pi by L. So this is the second result. Now let us apply the third boundary condition, dou y by dou t at x comma 0, 0. For this we need dou y by dou t first. So this is y, take the correct solution y and differentiate y with respect to t. So what is dou y by dou t? Differentiating y with respect to t. So the first term is this. Since c1 is 0, we have substituted c1 0. Now look at the term having t. Differentiate that. Cos, when you differentiate, minus sin pat into pa. Plus c4 sin pat when you differentiate, cos pat into pa. So this is dou y by dou t. Now substitute dou y by dou t at x comma 0. What is the meaning of x comma 0? The second coordinate is t. So t you have to put 0. So when you put t 0 here, what do you get? Here sin 0, 0. Cos 0, 1. So the final answer here will be C4 PA equal to 0. So from here, the condition says the final answer is 0. So from here, which has to be 0? C4 will be 0, because don't touch any term having variable, and PA are all fixed constants. So you should not touch them. So which has to be 0? C4 has to be 0. So third also we have applied. So now before applying the fourth condition, look at the fourth boundary condition. It is having a non-zero value. See, the first three are having 0, but the last one is having non-zero. So before applying any non-zero boundary condition, we need to generalize the solution. Now what is the meaning of generalizing a solution? Let us see. Before that, apply all the three results whatever you have got. So what are the three results we got? First we got C1 0. Next we got P equal to n pi by L. Next we got C4 0. So these are the three answers now we have got. Substitute all these three answers in your correct solution. So you will have y of x comma t is, this is the correct solution, C1 0. So second term is C2 sin px. In the place of p, substitute n pi by L. Yeah. In the second term, C4 is 0. So this is 0. And C3 into cos PAT. In the place of P, you substitute n pi by L. So you have like this. Now substitute C2 into C3, that constant, as a general constant Cn, and vary the value of n from 1 to infinity. This process is known as generalizing a solution. So when you generalize this solution, C2 into C3, I have to write Cn. C2 into C3, I am writing a Cn, and I am varying all the values of n from 1 to infinity. So I have to put a summation n equal to 1 to infinity. In the place of C2, C3, I am putting Cn. So into I have sin n pi x by L, into I have sin n pi x by L, and into cos n pi at by L. So this is known as most general solution. In this most general solution, we need to now apply the last boundary condition, y of x comma 0 equal to k into Lx minus x squared. Now what is y of x comma 0? Go to this y of x comma t. The latest one is most general solution. Go to that. Put t 0. Yeah, in the place of t when I put 0. So here I have t. When I put 0, cos 0 will become 1. So y of x comma 0 will be summation Cn sin n pi x by L. And the boundary condition says that is equal to k into Lx minus x squared. And now look at this. What can you observe here? What is this? Remember your half range sine series, what we had already studied in last unit. Yeah, this is the half range sine series, sigma bn sin n pi x by L, where bn has a formula. So is it not resembling the same? Yes, so it is the same half range sine series. So comparing with half range sine series, we have the formula for Cn is the same formula of Bn what we had there. So the Cn formula is 2 by L, 0 to L, f of x sin n pi x by L dx. And what is this f of x? K into Lx minus x squared. So now you know how to use Bernoulli's formula. This is integral of two terms. So taking k out, keep the first, integrate the second. Sin when you integrate minus cos. Minus differentiate the first, integrate the second. Plus differentiate the first, integrate the second. So using Bernoulli's rule, you can integrate this and you can apply the limit. In the place of x, you have to apply L, minus in the place of x, you have to put 0. So you will get the answer of Cn like this. This answer of Cn finally you will have 1 minus minus 1 power n. So whenever you have like this, you have to segregate. So this you have to substitute in the